Okay, so now we move to the second part of our lecture, right? In the first part, we had a general discussion on what is deep learning, how it resembles human brain, what are the different deep learning data sets, and what are the different deep learning libraries, right? And towards the end, we discussed that how you can do some basic installation and you can write a hello world in Python, and how you can install libraries like TensorFlow and create environments, okay? So in the next half an hour, I'll try to wrap this discussion up. I need to introduce you to some preliminary concepts which will be repeatedly used in almost every lecture or every discussion, right? So I'm spending about 30 minutes on this. For some of you, these could be quite basic, but for others, these could be something that they were not very clear about. So I want to make sure that we are all on the same page when we come next week and we start with neural networks, right? So there are diverse concepts which may not be directly related to one another, right? So you will see one concept A, then concept B, then concept C. So you might be thinking that how they are linked together. So they are not linked together, but they are linked to the subsequent discussion that we'll be having in all the, you can say, neural networks or convolutional neural networks and so on, right? So let's go into more technical details. So these are few things that I need to discuss, right? The most important is derivative and computation graph, right? Because when you are doing back propagation, you have lots of derivatives and you have lots of computation, right? So these are the critical ones. Then there are very simple ones, and I hope the last two bullets are fairly simple. So maybe you already know one hot encoding, sigmoid, softmax, because almost in every lecture I'll be using sigmoid, softmax, right? So if you know these, I can skip them, right? But if you say we'll touch these as well. But primary focus is on the first two bullets, derivatives and computation graph, okay? So you see, when we say derivative, what does it mean? Okay, maybe let me shift to board maybe, and I can explain better, right? So most of this content is based on, you can say you have some material by the course Google Udacity, and there's another course by Andrew Nick, right? So some of the content that you will see in these slides, it has been borrowed from these sources, and you can see the citation in the bottom of the slides. Okay, so maybe let's go to the board and discuss, okay, because otherwise on slides it will be pretty boring. Okay, so we need, someone ask you, okay, you are an expert of deep learning, tell me what is derivative. Okay, so, okay, what could be the simplest answer if someone asks you derivative? What is the synonym of derivative you can tell? Can someone quickly type in the chat box? One word answer of what is derivative, one word. You are not allowed to use more than one word. Can anyone tell me one single word which you can use in place of derivative? It has to be one word, not two or three. Okay, I'll wait 5 seconds and then I'll proceed. Okay, derivative is change. Yes, very good. Derivative is change. Okay, and any other suggestion? So you see, for derivative, we use different, you can say, things, change, or another slightly technical but still synonym is the slope. Okay, so derivative is just a fancy name for change, you can say, or if you want to be a little technical, you can say slope. Derivative is nothing but a slope. Now what does that mean? Maybe does not make much sense, so let's go into more details. Okay, let me make a function, and I will make the same function which is in the slide so that we can correlate. Okay, so okay, this is A, and here I have, I say, okay, f of A is 3A. Okay, so it will be a straight line, and it will be maybe a straight line like this. Okay, I could not draw it perfectly, but it is a straight line. Okay, and this is your function f of A. Okay. Okay, now just we are discussing what does it mean when we say derivative is slope? What does it mean? Okay, so for that, okay, I take a point here, say this is 2. Okay, so I say, okay, a is 2. So when a is 2, I am interested in finding out, okay, what is f of a? Means what is the value on the y-axis? So what is the value here? So you plug in this equation, 3 into 2 is 6. So when a is 2, f of a is 6. So it means that this point is actually 6. Okay, fair enough. You do it in class 9th, I think, even before that. Okay, now what we do is we say, okay, let's change the value of a by a very, very small amount, right? For example, if it's 2, I increment it by a small amount. Say that small amount is 0.001. Okay, theoretically, it is much smaller than this. It is very close to 0. But since numerically, I cannot write like 0.00001, so I'm just putting 2 zeros, right? The idea is that we increment it by a very, very small amount. Okay, so maybe I can draw it here. This is 2.001. So I'm interested that when I increase the value of a by a very small amount, what is the impact on f of a? It means I'm now interested in, okay, what is this value? Okay, so you can plug in here and it will come out to be 6.003. So in other words, right, what we are saying is, let me just change the color of the ink. Okay, so you see this part, how much is this? This is actually 0.001. And this part, this is actually 0.003. Okay, sorry for the bad handwriting, but I think it makes sense. Okay, now is the important thing. When we increased a from 2 to 2.001, okay, when a goes up by a small amount, we say how much f of a goes up. F of a goes up by this amount. And this number is actually 3 times this number. Okay, if I multiply it by 3, I get this. So in other words, I can say if I increase a by a small amount, f of a increases 3 times as much as the increase in a. Means a is being increased by 0.001 and f of a is being increased by 3 times of 0.001. Okay, and now if we see it geometrically, what is actually happening? This is, I have not drawn it very neatly, but actually this is a right angle triangle. So let me just redraw it. Okay, this is 0.003, this is 0.001, and you know, how do we know that this is 3 times of this? You simply divide the two. If I'd say 0.003 by 0.001, I actually get 3. Okay, but now if you see it from the perspective of geometry, what actually you are doing? Okay, so you see this is a right angle triangle. You are dividing this, sorry, you are dividing this by this, yes, and this is called perpendicular, this is called base. So when you are doing this, you are actually computing tangent of this angle, right? And what is this? This angle is actually the slope. It is telling you how much steep is it. For example, if it comes out to be 1, it means it is a straight line at 45 degrees, right? Since this is not at 45 degrees, this is some greater angle, so that's why the slope is 3. If I increase it further, it comes out to be maybe 4 or 5, then of course this line would be much more steeper. Okay, it's like that you are climbing a rock or a mountain. So if it's at an angle of 45 degrees, it's relatively easier for you to climb. But if it is like 70 degrees rock, then definitely it will take much more effort because it is much steeper. So you see, what is this? In other words, we say, if I write it mathematically, I can say derivative of f of a with respect to a. This is the fancy term, but what I'm trying to say is that when I change a slightly, the change in f of a is 3 times. Or in simple words, I can say that the slope of this function at this point is 3. It means if I compute the slope of the function here, the slope is 3, right? And we are talking about this place, which is a equals to. Of course, we can compute slope of this function at some other location, maybe a equals 5, and we see what happens there. Okay, so this is the general idea. Now let me go back to the slides and then we do rest of the discussion there. Okay. Yeah. Okay, so you see, this is the same, but a cleaner version of what I was trying to say. This is your function f of a. So when a is 2, f of a is 6. If we increase a little bit, f of a increases to this number, right? So as I told you, if we are interested in computing that how much is the change in f of a when we increase a, you simply divide these two, so you get 3 as an output, right? And we can say that the slope of f of a when a equals 2 is 3, or you can say the derivative of f of a when a is 2 is 3. And if you want to write it mathematically, you can use simply this notation: derivative of this function with respect to variable a, it is 3. Okay, now we change the value of a. We see what is happening when a is 5. So when a is 5, f of a is 15, right? 3 into 5 is 15. When I slightly change the value of a, f of a becomes 15.003. So again, if I divide these two, I get 3. So it means that the derivative at a equals 5, here also the slope is same, which is 3. And now you can generalize that since it is a straight line, so if you find the slope of, you can say here, or here, or here, it is making the same angle with the x-axis, right? That is why the slope or the derivative of this function at every point is same, which is 3. And if you remember the formula from the calculus, if you take derivative of 3x, it is 3. Here we have, instead of x, we have variable a. So if you take derivative using, not using this numerical approximation, but using the calculus formula, you know very well that derivative of 3x is actually 3. So it is actually telling you that it is a constant value. It means since it is a straight line, so no matter where I compute the slope by making a small triangle like this, I will always get the same value. You see, because it is always making the same angle with the horizontal. But this may not always be true, right? And as we'll see in the next example, okay? So for this example, it's a straight line. So we have the same slope at all the points. But what will happen if we have a function like this? Okay, we have like f of a is a square, okay? So now we do the same exercise. Say when a was 2, f of a was 4. When I increase a by a small number, f of a, when I take the square, I get 4.004. So when a is changed by a small amount, the increment in f of a is 4 times this value. So I can say that the derivative of this function at a equals 2 is 4, right? You can see when we say derivative, we are talking about how much steeper is this line, what is the slope of this part, okay? What is the slope of this small triangle? But you can already guess that if I now make a triangle here, then you see this would be more steeper. If I make a triangle here, this I have a slope like this. Here I have a different slope. So if it's a quadratic function, which is the case here, the slope will be different at different positions on the function. That is why if we compute the same, you can say thing by changing the value of a, it means I'm talking about somewhere here. So I expect a greater value because the slope would be higher. So you see, when you plug in the values when a is 5, f of a is 25, but when you increase a by a small number, this is 10 times of this number. 0.010 is 10 times of this number. So it means we are saying that when a equals 5, the derivative of this function is 10. So here the derivative was 4, here the derivative is 10, and as you progress, this slope becomes, this function becomes steeper and steeper. So that's why you have an increasing value of the slope. So in general, we can say that the slope of the function is different at different points, right? And again, instead of these computation, if you also, if you use the formula, so you know that if you have x square, if you remember the derivative of x square was 2x, so you can directly compute the derivative using this formula, you will still get the same thing, right? That if I'm computing derivative at 5, so 2 into 5 is 10. And if I'm computing derivative at x equals 2, the derivative is 4, which we computed on the previous slide. So this numerical approximation is giving us the same result that we computed from the formula of the calculus, okay? And just one more comment before I conclude this discussion on derivative. We again switch back to the board. You see, if you remember, or if you go back and search some book of calculus of maybe first year or metric, so this is the definition of derivative you will find in the books. it is like x plus delta x minus f of x and divided by delta x, and इसके साथ लिखा होगा limit delta x tends to 0. This is, if you search on Google or you open up some book of calculus, this is the definition of derivative you find. And you see it is exactly the same thing that we did. When we have a function, delta x in our example was 0.001. But actually delta x has to be a very small value which is close to 0, right? So you computed the value of the function at this point, okay, which is actually the first term. Let me just change the color so that it is visible. So you computed this, which is the value here, and then you computed this value, which is the value here. You subtracted these two, okay, means you have one value here, one value here. So maybe in one of the cases we got 0.003, and this is delta x, which in our case was this thing, which was 0.001. So you see, this is how we actually computed. But the definition of derivative, the calculus version of derivative, is also asking you to do the same thing. The only difference is that we assumed 0.001 as delta x, but the definition says that it has to be a very, very small number. Maybe it's a number like, say, something like this, okay, which is very, very close to 0. Okay, so now let's go back to the slides and see what else do we have there. Okay, so you see, this is, I think we have already discussed. So you can extend the same idea to different functions, right? For example, you can do it for a cube, or you can do it for log, and you can convince yourself that every time you compute derivative numerically or using a formula, you end up with the same thing, right? So this is basically what derivative was. So the summary is that if you have a straight line, so you have the same slope at all the points. So that's why you have a fixed derivative at all the points on the line. But if you have a curve, then depending upon whether it's a square or a cube or a4 or whatever it is, you will have different value of slope at different points. Right? So next we have a computation graph. But before that, if you have any quick query related to derivatives, please let me know. Else I straight away move to the next topic, which is computation graph. Okay, so computation graph that we'll see now is something that will be very frequently used when you are doing back propagation. Okay, so that's why it's a good idea that we kill this topic for once, so that when we are discussing back propagation, we don't have to revisit it time and again. Okay, so you see here you have a function, we are calling it j. Sorry, and we have three variables, right, which are a, b, and c. Okay, and we want to compute this function 3 times a plus bc. Okay. So we have defined certain variables that, okay, first we perform b into c, so we use a variable v, and then we add this to a, so a plus v is actually, we are calling u, and then 3 times this thing is actually v, so we are calling it 3v. Okay, so we have just taken some variables, some additional variables to solve this problem. So the first operation that we'll do, what is that? We will multiply b and c together. Okay, so just like you make a tree in data structures, right? So you have b and c, you multiply them together, you get the product, which is u. Okay, and whatever is the answer of this product, you add a to it, a plus bc, and we are calling it v. So these are just two new variables we have introduced. And finally, once you have solved this, you multiply it by 3 and you get j. So we say j is 3 times v. Okay, and just to make it a little bit more intuitive or easy to understand, instead of dealing in terms of variables, we have numbers like, we assume a is 5, b is 3, and c is 2. Okay, and then we have computed these numbers. So 3 into 2 is 6, 6 plus 5 is 11, 11 into 3 is 33. So for these values of a, b, and c, j comes out to be 33. Now what we are trying to do, we are actually now will be applying our definition of derivative to this computation graph. Okay, and our objective is that, okay, if I change something in v, how will that impact j? Okay, we already have seen how to do that, and we'll just be repeating. But an additional thing that we'll see is that what will happen if I change a? How will it affect v? Now, why is it different from the previous example? Because you see, now j is not directly dependent on a. J is dependent on v, and V is actually dependent on A. So it's like you have a chain that first you will see how J changes with respect to V, and then you will see how V changes with respect to A, and then you will combine these two pieces of information, and you will be in a position to tell that if you change A, what will be the impact on J, right? And this chain could be, here the chain is fairly simple, you have only two levels, but this could be a very you can say hierarchy, right? What you will have in the neural networks. Okay, so first do something very simple. Okay, we say we are interested in computing dj dv. It means we are interested in finding out how j changes if I change v. Okay, so we know that j is 3v. Okay, so when v is 11, j was 33. Okay, this we already know. If I have to find derivative, what do I do? I have to find derivative with respect to variable v. So I will slightly increase the value of v. So I will say, okay, let's make v equals to 11.001. And how j will change? J will become 33.003. So now you see, again, you can see when I increase v by 0.001, the increase in j is 0.003. So you can easily compute the derivative, which is like 0.003 by 0.001, and you can say this number is actually 3. So you have computed derivative, and if you don't want to do all these calculations, you can simply apply the calculus formula. You still get 3 as the derivative, right? Derivative of 3v is v, derivative of 3x is x, is the, sorry, is 3, is the same thing. Okay, so these are the same calculations which I just did. Okay, now slightly change the problem, right? We say, okay, how J will change if instead of changing V, I change something in A. It means now we are interested in computing dGA over dA. Okay, so first let's try do it with the conventional way, which we know that what we know from our previous knowledge is that, okay, when A was say 5, what was J? It was 33. Now I will change the value of A, not any other variable. Why A? Because I am computing derivative with respect to this variable. So actually, when I will change A, this V will change. Okay, when A becomes 5.001, this will actually become 11.001, and this will actually become 33.003. So it means this will again come out to be 33.003, and I can say that this number is actually 3. However, if you observe, actually A is not directly influencing J. What is actually happening is that J is dependent on V, so I can compute the derivative of J with respect to V, and V in turn is dependent on actually A. So this is how I can, you can say, write it in another form, that if I'm interested in computing derivative of J with respect to A, that if I change A, what is the impact of J? I can break it down into two, you can say, steps, that I study how J changes with respect to V, because J is dependent on V and V is dependent on A. So this is what we call in calculus the famous chain rule. Okay, and if we do it, you already know what is this. We computed it in the previous slide. This was 3. Now let's compute this dv over da, that what will happen if I change A. So you see, when A was 5, B was 11. Yes, and when A becomes 5.001, V becomes 11.001. Okay, so the change here and the change here is same. If I divide this by this, I get actually 1. So it means this number is 3, this number is 1. Sorry, not 3, this number is 1. And when you multiply them together, you get 3. So you see, derivative of J with respect to A is 3. We computed it directly using this, and we computed it indirectly using the chain rule, and we are getting the same thing, right? So in this case, it was a small computation graph, so you could compute directly. But practically, when you have these levels, these would be actually different layers of the neural network, right? Maybe you have 3 layers or 10 layers. So that's why when we are deriving something, we will not be doing it numerically. This is just for understanding purposes. We'll always be using this chain rule. Okay, so just to show you a cleaner version of this, That's if I have to compute derivative of j with respect to a, I can split it into two derivatives and I get back the same thing which I obtained directly. Okay, one more example and then I conclude it. Okay, so in similar way, you if someone asks you how do you compute derivative of j with respect to u, okay, so you can actually break it into two problems that j is dependent on v, so I will compute derivative of j with respect to v, and v is dependent on u, so I will compute derivative of v with respect to u, and then I get the answer. Okay, I'm not solving it because you already get the idea, so I will just save some time. And again, as I told you, the chain could become longer as you keep on adding levels, right? One last example that I'm interested in finding, if I change B, how it will impact J. Okay, now we have three levels. So first I see how J changes with respect to V. Then I see how V changes with respect to U. And then I see how U changes with respect to B. Okay, and using the previous discussion, you can compute all of these terminologies, which are 3, 1, 2, so it comes out to be 6. So in other words, we are saying if I slightly makes a small change here, right, the impact here would be 6 times more than what I changed here. Okay, so this is actually what it is trying to say. When B is increased by this, the increase in J is 0.006, and this number is 6 times of this number, right? So just a recall of what we mean by derivative. Okay, so please do remember this discussion because this will be repeatedly used in the subsequent discussion, especially once we are doing backpropagation. Okay, so is there any query, any comment, quick comment? Because we have some time left, so I'll just quickly wrap up. If there is no comment, I'll move forward. Okay, so that was it for computation graph. Now I quickly introduce you to something that maybe theoretically you will not be using it that much, but you will be using it once you are implementing things, right? That you see in machine learning, you must have seen some classification problem, right? For example, if you are shown a picture and you have your system computer has to discriminate between two fruits, right? So maybe there are pictures of like apple and then there are pictures of like pear, I don't know, maybe this is a pear, right? So there's a classification problem. So once you design a neural network to solve this problem, there are two classes, right? And you have to give them label. So normally labels have to be numbers. Labels cannot be string, right? So this is a string. These are all string, but we want to convert them into some numbers because neural network only understand numbers. It does not understand strings. Okay. So a very common way that you will be mostly using is called one-hot encoding. Now, what does it mean? That it simply means that suppose you have an image of an apple, okay, and I want to convert it into a number. Since I have two classes, so I will have a vector of 2. Okay, this first position is for apple and this second position is for pear. So if it is image of an apple, I will put a 1 here and a 0 here. If next one is an apple again, I will put 1 here, 0 here. If it's a pear, I'll put 0 here and 1 here. It means one hot simply means that this is one vector in which there is only one value which is 1 and rest everything is 0 because one object can belong only to one class, right? So maybe it is not very intuitive to understand from a 2-class problem. So maybe from a 3-class problem it will make more sense, right? Let's suppose you have 3 classes, red, yellow and green. Okay, so since we have 3 classes, so every vector will have a length of 3. You see you have 3 values. If my first object is of red color, okay, you have to tell the machine is shown different shirts and machine has to guess what is the color. Okay, so if I have a shirt which is red, so I'll put a 1 here and 0 here. Similarly, if there is a shirt which is yellow, I will have a 1 here and here I have zeros. Okay, so you see it is a very common representation, and now this terminology one hot will make sense. One hot means that only one value is active, rest everything is passive, rest is 0, it is dead. Okay, so there's one downside to this representation that you see, suppose I have 1000 classes. So this representation is very sparse. Sparse means that if I have 1000 classes, there are so many zeros, like there will be 999 zeros and there is only one value which is 1. Okay, so it will take a lot of memory if I have 1000 classes and I have 1 million images. Okay, so you can guess that this matrix would be of this size. So it will take quite a lot of memory just to store the labels. Okay, so but still this is a very simple notation for the machine to understand. So most of the time that we are doing some implementation, we'll be using one hot encoding. But of course, there are other ways that we'll see once we actually implement it. Okay, so next, another thing that we'll be using very frequently is called the sigmoid function. Again, you must have seen it in machine learning, but I'll quickly revise it, right? That this is a very common function that we'll see with neural networks. Why we see it, that we'll discuss later. We are only discussing what is this function doing, okay? Why we are not talking right now. So this is a function, this is the equation that if I have, say, x variables, f of x is like 1 over 1 plus e raised to power minus x. Now the beauty of this function is that whatever value of x you give to it, it will compress that value in the range 0 to 1. And you can verify that suppose you give a very large positive value. Okay, so what will happen? This is negative, so this number would become close to 0. Okay, and you are doing 1 divided by 1, which is like 1. So if you have a very high value, you will get a very close to 1. If I give a very large negative value, what will happen? This minus and the minus would cancel out. So I will have 1 over a very large value, and this would be close to 0. So if I give it a very large negative value, I will get something which is close to 0. So you see, whether you give it 10 or you give it 10 million, right? Your output will never go out of this range. And this is something very useful, right? Because in neural networks, we don't want our values to be very large or very small. So if we are using this function at different parts of a neural network, we are actually making sure that every time I do some computations, my values remain within a manageable range. And that range for this function is 0 to 1. Of course, you have other functions which give you value in -1 to 1 and so on, right? Okay, this I'll skip. I'll do it next time, right? This is a derivation, so let's skip it. I'll just show you one last thing and then we'll conclude. Okay. Another function, just like sigmoid, I'll be frequently using is the softmax function. Okay, and it's very important that you understand what is softmax. Okay, suppose you have some classifier, any classifier, SVM, KNN, whatever you are talking about. You give it some data, okay, and it has to tell you whether it's a cat or it's a dog or it's a horse. Okay, so normally classifier will give you raw scores. Raw scores means, for example, here the score is 2, maybe here the score is 4, and here the score is 0.5, sorry, okay, something like this. And we want to convert our scores into probabilities, right? Because if you have probabilities, then they are very easy to interpret. Because if you see this number 2, we don't know whether it's a very high number or whether it's a low number, right? Because unless we know what are the other numbers, we cannot guess whether it's a high value or a low value. But once you convert into probabilities, you know that the sum of the probabilities is 1. So this 0.7 is telling you that your algorithm is 70% sure that this object is a cat. It is 20% sure that it's a dog, and it is only 10% of opinion that it might be a horse, right? So decision making becomes much more crisp. Now, and how do we implement this function? You just have e raised to power, suppose I want to convert it into probability, e raised to power 2, and then here you have the sum of all of these, e raised to power 2 plus e raised to power 1 plus e raised to power 0.1, right? So you have just e raised to power the score which you want to convert to probability, and here you have the sum of all the scores, of course, with e raised to power. Now you can say that why are we doing e raised to power this? There's another way of normalizing it, that I can simply add these values together, okay, and I can divide every value by this sum. If you do that, you still have values in the range 0 to 1, and if you sum them all, you get 1. Then you might think why we are doing this thing. Okay, so the answer to that comes in the next slide. That suppose there's a classifier which has to tell whether it's a cat or it's something else, right? So suppose the classifier gives you two numbers, 1 and 2, okay? And if you apply softmax, okay, so this 1 will become, I think, 0.26, and this 2 will become 0.73. On the other hand, if these numbers were, say, 10 or 20, okay, then you see this score will become very close to 0, and this score is almost close to 1. So if you interpret it intuitively, when your classifier is 70% sure, right? Maybe it is not a very clear, crisp image of cat. Maybe it's a blurry image of cat, so the algorithm is 70% sure that it's a cat, but 30% or 25% it thinks it might be something else. But now once you have 10 and 20, okay, then your algorithm is very, very sure that it's a cat, and it is very sure that it is not something else. Okay. Now, if you do the same thing with standard normalization, by standard normalization, I mean that instead of softmax, if you do this, okay, and means you simply add them and divide them. So when your scores were 1 and 2, if you do this normalization, you are getting 33% and 66%. And if your scores were 10 and 20, you are still getting the same confidence score. So you see, when you are normalizing, it is not taking into account the difference between these two, because you are not doing this thing, e raised to power score. You are simply adding things and normalizing. On the other hand, when you are applying softmax, so actually what is it doing? If the difference between the scores is it thinks is relatively large, so it will be more confident on the decision that it is taking. On the other hand, as you saw at the bottom of the slide, that if we are doing standard normalization, then the confidence does not change whether you have 1 2 or 10 20, or even if I have 1000 and 2000, or even I have 1 million, like maybe 10 million and 20 million, you still get the same confidence scores. But this is not the case when you are using softmax, right? So with that, I'll stop here, right? We are left with one derivation, but I'll do it in the next week, right? So if you have any comments, any queries, just quick ones, please let me know.